Okay, so probably one of the biggest things that most students have a hard time with in the urinary system is the countercurrent multiplier and exchanger and how urine is concentrated. I think I did this in office hours probably 3 or 4 times, and I still had people ask me questions about it. I know it's a very complicated process. Okay, so I'm going to try to make this video short and sweet, and then I'll try to post something that I did previously where it was a little bit longer to explain the whole process. I don't want you guys to have to try to figure out the whole process. I just want you to understand the basics of the purpose of it. Okay, the purpose of the countercurrent multiplier is to create an osmotic gradient in from the renal cortex to the renal medulla. And it's very, very difficult to draw this, to simulate this. It just is, okay? I've drawn it a couple times and it just doesn't kind of work out very well. It's something that you really need like a really great animation. I don't think anybody has ever really made one. But the purpose of this is, again, you want to create an osmotic gradient or a salt gradient going from the cortex to the medulla. Okay, so from the cortex to the medulla, you want to have like less sodium concentration to all the way down here towards where the minor calyx is. You want to have like really high sodium concentration. Okay, it doesn't matter what the numbers are. I'm not going to ask you questions about the numbers, but if it helps you, you want to think about like 300. So 300 means like 300 milliosmoles means there's a little bit of salt compared to water. But then over here, I'd have like 12 to 1400. So that means there's a lot of salt and not a lot of water. Okay, if that helps you. Just think about that gradient is going to go from low to really, really high in the deepest part of the medulla. I have to set up this osmotic gradient. So I'm going to need to do two things, or really I need two things. One, I need the nephron loop, and two, I need the vasa recta, okay? The nephron loop is going to be the countercurrent multiplier. It's a countercurrent multiplier because it's going to multiply this number here to get it to all the way to that number, all right? Then I also need the vasa recta. The vasa recta, this is my vasa recta. The vasa recta is going to be the countercurrent exchanger. Basically, you're going to exchange solutes back and forth with blood without changing that gradient right there, okay? I have to do this to help me maintain homeostatic balance, and because the capillary is there, it's permeable to everything. So what we're going to see is our filtrate, remember, is going to come through the proximal convoluted tubule, and when it does, you're already going to pick up sodium, and remember, water follows as a result of that, okay? So in the capillary, we should have like sodium and water being reabsorbed. And as a result, when you hit the descending limb here, you really shouldn't have too much salt in your filtrate, okay? This is my ascending limb. Now, this is really a weird concept, but you have to set this up, and then it's going to run for your lifetime. So how do you set this up? You're going to set this up basically when your kidneys come online at birth, okay? So the first thing you're going to do is you're going to create the filtrate. The first run of the filtrate is going to come through the descending limb. The descending limb is only permeable to water. Remember, we're here. We're only reabsorbing water at the descending limb, and we're only reabsorbing sodium at the ascending limb, okay? But if this is the very first time my kidneys have kicked in, I don't have that gradient over here. I don't have this gradient yet. I have to create it. So as my filtrate comes up into my ascending limb, what's going to happen is some sodium pumps turn on. And essentially, those sodium pumps are going to cause the filtrate to move sodium. It's not going to cause the filtrate. It's going to cause the ascending limb to push sodium or pump sodium out of the ascending limb and into the interstitial space, okay? So the filtrate down here is gonna sit here for a while, and you're gonna move some of the sodium out. And then it gets pushed up and you move more sodium out, you get pushed up and move more sodium out. You push up, you move more sodium out. So basically by the time you've reached the top of the ascending limb, you're gonna have a lower sodium concentration. Why? Because you pulled it all out, okay? That's why. So I have less sodium and I'll have more water. So now I started creating a sodium gradient in my interstitial space, okay? So here I'll have less sodium because I didn't pull so much out here, but here I'll have more sodium because again, this is where I'm gonna pull more from, okay? And then I'm gonna have my second round of filtrate coming through. So just imagine this is my second round of filtrate coming through. Now the descending limb is permeable to water. Here's one of the biological principles that you need to understand though. Water really only moves if there's a concentration gradient of water. The only way to have a water concentration gradient is by adding solutes or salt. Really any solute, but usually we talk about salt, okay? So now because there's a sodium gradient in the interstitial space, as my second round of filtrate comes through, I'm gonna start to reabsorb water in the descending limb. And you just wanna think about, okay, so remember here, we're gonna have like not a really high sodium concentration entering. This is a low sodium concentration. This kind of got a couple students like, they didn't understand why. Remember, we're reabsorbing sodium and water at the proximal convoluted tubule. So since we're doing that, everything that's entering the descending limb is gonna have less sodium because I have reabsorbed a whole bunch of it, okay? You might be thinking, how come I didn't reabsorb as much water? You don't reabsorb as much water at the proximal convoluted tubule. So as my sodium concentration is low coming into the descending limb, I'm going to pull water. I'm going to move my filtrate, pull water, move my filtrate, pull water, move my filtrate, pull water. So by the time I get down to the bottom of my descending limb, I have a really super concentrated filtrate, meaning I have way less water and a hell of a lot of salt, okay? So that's not a very good thing, basically. So as you go and you push your filtrate through the loop of Henle, so the loop of Henle is not permeable to anything. We're gonna push our filtrate up through the ascending limb. And again, since we're super salty, we're gonna pump out sodium. So I'm gonna move that sodium out so that I have less sodium in my filtrate, basically as it goes into my distal convoluted tubule, okay? And this is gonna help me create that osmotic gradient, going from a really low concentration of sodium to a really high concentration of sodium from the renal cortex to the renal medulla. So like round 3, as the filtrate comes through, you pull water from the descending limb, push the filtrate up through the ascending limb, pull salt, push it through the distal convoluted tubule. And this happens over and over and over and over again. As it happens over and over and over again, you maintain this osmotic gradient in the interstitial space, okay? And I want that osmotic gradient because I need it in order for me to reabsorb water when I'm dehydrated. That's this whole urine concentration thing, okay? This is why the kidney is gonna be salty from the, super salty on the middle part, okay? That's the whole purpose. This whole purpose of the countercurrent multiplier is to concentrate urine if you're dehydrated or you're hemorrhaging, all right? So I created this concentration gradient, but now what we have to account for is, I was gonna think about like what colors I'm gonna use. I'll just continue with black. And we have to account for the vasa recta is also permeable. The vasa recta, unlike the renal tubule, is permeable to everything. So remember, the renal tubule is selectively permeable, meaning only water gets reabsorbed and only salt gets reabsorbed, because that's the only thing that will move through the tubule on each of these sides. However, the vasa recta is not like that. So because there's a lot of salt in the ascending limb, essentially that salt ends up in the vasa recta and you pull water out of the vasa recta near the ascending limb of the nephron loop. Okay, it might be like, well, yeah, blood's flowing in that direction. Blood's flowing in the opposite direction. Okay, I know some of the pictures in the PowerPoint might not show this in this way, but blood has to flow in the opposite direction. So you might be thinking, isn't this counterproductive? Yes. You want that salt to be in the middle part. And if we put too much water in the interstitial space, then it's going to counteract our osmotic gradient. So that's why as we move blood through the vasa recta, again, what's going to end up happening is when that blood flows over to the descending limb, now what it's going to have is way too much salt and not enough water. So now the water that we pulled out of the descending limb will go into the vasa recta, and we will start to pull out salt. Whoops. It's not what I want to do. We're going to pull salt out. Okay. And you're probably basically thinking, didn't we just do this but in reverse on the other side? Yes, we did. So the purpose of the countercurrent exchanger is to maintain the osmotic gradient. You basically want whatever is happening on this side to be counteracted on the other side. Because you can't tell the vasa recta to not be permeable to things, it's going to move stuff back and forth. So we're going to pick up sodium, we're going to release water on one side, get super salty, and then that's not good for blood. So we're going to push water in and pull sodium out so that blood maintains its consistency of water and salt. And this also helps to make sure that our osmotic gradient is maintained as well. Because basically, you're exchanging substances, but you're counteracting what you did, okay? That's what you want to think about. The vasa recta is going to pull stuff back and forth, but it's going to negate or cancel what it's actually doing. That's the purpose of the exchanger. It's exchanging water and sodium. That's why it's the exchanger, okay? The multiplier multiplies the amount of salt in the interstitial space. All right, I know that was probably a lot. But now let's think about why you want this osmotic gradient, okay? You want this osmotic gradient because you want to be able to concentrate urine. So if you cut your collecting duct, into two parts, we're going to think about what's going to happen if you're normal versus if you're dehydrated, okay? So you want to think about this is hydrated on this side, and this is dehydrated on that side, okay? If you're hydrated, what's going to end up happening is you have a really low sodium concentration entering the collecting duct, and you're going to have a high water concentration entering the collecting duct. I kind of made my sodium in a weird way. So let's do this again. So I have a low sodium content entering the collecting duct and a high water content, because that's just how volume works. Whatever's the lower one, the opposite has to be the higher one, okay? So if you're well hydrated, what ends up happening is your filtrate just is going to go through the collecting duct with no problem, and you end up with either a really large urine output or a normal urine output, okay, because you're hydrated. In this case, the collecting duct is only permeable to water or permeable to salt because of hormones. So if you don't have many hormones that are being released, you're just going to release all your filtrate. If you're dehydrated, though, what ends up happening is ADH, gets released in higher quantities, okay? As ADH gets released in higher quantities, it targets the collecting duct. And when it targets the collecting duct, it puts something called aquaporins, which is basically water channels, into the collecting duct. And because you have this concentration gradient here going from the cortex to the medulla, you're going to start to move water into the interstitial space, which will end up going into the capillaries. You're reabsorbing water, okay? So remember, you can only pull water if you have two things. You have to have ADH because you have to have those water channels. And two, you have to have a salt concentration gradient. You have to have an osmotic gradient because remember, water only moves if there's an osmotic gradient or if there's solutes present. So we're going to continue to pull water. And as we do, the amount of salt increases in our filtrate. Okay. And since the salt increases in our filtrate, the salt has to increase in our interstitial space. So the salt is higher in the interstitial space so we can suck water out. Right? Because you have to have a gradient. So basically, if you have a low sodium here, I know that's a little bit small, and you have a higher sodium here, that's still going to allow me to continue to pull water, because here I would have a low sodium, but hopefully lower than the outside. And here I would have a high sodium, but hopefully lower than the outside, because you have to be able to pull water if there's a concentration gradient of salt, okay? Which means that as you pull more and more water out, urine output decreases. So that means you won't have a whole lot of urine, okay? I think this kind of got you guys maybe in lab, or it might get you in lab depending on when you're viewing this video, because you had a little bit of trouble with like when you drink sodium bicarbonate. But think about, you have a lot of sodium in blood, okay? You can secrete that or just not reabsorb that sodium, but also what that means is you have less water in blood. So you're actually dehydrated. And because the renal tubule is only selectively permeable in most cases, then you have to reabsorb water to make sure that your blood salt concentrations go down. That's why. This is also why you shouldn't drink seawater, because seawater actually dehydrates you. Then you have urine output is like next to nothing, and you keep drinking seawater. Ew, don't do that. Okay, don't. If you're ever lost at sea, don't do that. Okay, so I'm hoping this helps a little bit with the countercurrent multiplier and the countercurrent exchanger and what is essentially happening. It's a very complicated process, how these numbers change. That's why I got rid of the numbers. Okay, but I'll throw up another video from a previous semester where I went over it in much more detail, if you're interested.